This is paper presentation about dynamic memory management in massively parallel systems, such as GPUs. So GPUs have become an indispensable component in today's high-performance computing systems and have shown great values in many compute-intensive applications. And there is a strong movement of developing software systems on GPU, such as database management systems, graph analytics, and data analytics. And there are unique challenges in developing system software on massively parallel hardware, mostly imposed by the need to support a large number of parallel threads and the architectural complexity of GPU hardware. Dynamic memory allocators face challenges such as thread contention and synchronization overhead. And multiple studies have proposed solutions to address these challenges. And similar to traditional memory allocators, such solutions utilize a shared data structure to keep track of available memory units. And so existing memory allocators maintain a global state, such as a head and tail of a queue, to keep track of available memory. And so the allocation operations have to access such states in a protected manner. And the protection can be done via software lock, such as mutex, and so with latency at the 100 millisecond level on a CPU-based system. And hardware supported mechanisms called atomic operations are widely used to relieve such a bottleneck. However, while used in GPUs, this strategy still carries excessively high overhead. And although fast atomic operations have to be executed sequentially in case of conflict, the large number of concurrent threads in GPUs lead to a long waiting queue in atomic access to global states. So this figure reports our collected data for the average latency for performing an atomic operation against one global integer under the varying number of concurrent threads. And clearly the average latency per thread grows linearly with the number of concurrent threads. So in this paper, we present a high-performance memory allocation framework for GPUs. And unlike traditional wisdom that involves global states, this is a fundamentally new solution that carries very little overhead in allocating memory and is almost free for releasing memory. Instead of keeping any global state explicitly, we let the threads statistically find the locations of available memory via a random algorithm. And we developed analytical models to demonstrate that our method achieves symptotically shorter latency than the state-of-the-art GPU memory allocators. We also report a number of techniques to further optimize the performance of random method. Specifically, we present the use of Bitmap to reduce the number of expected steps needed to find a free page by a factor of 32 and 64, and a page sharing mechanism among neighborhood threads. And based on these techniques, we also developed an algorithm for serving requests of multiple consecutive pages. The performance advantage of our solution is fully supported by extensive experiment, such as so in a unit test environment, our solution was found to deliver a speed of up to 2 orders of magnitude over the current best existing solution. So a little bit of background on dynamic memory management on CPU. Memory allocators on CPU have been well studied since the 1960s, and some of the most popular mechanisms include sequential fit, which is a single linked list of all free pages, segregated free list, buddy system, which is a multiple memory pools of power up to in size, indexed fit, which is page information indexed in an array, and bitmap fits. And some popular implementations include the GNU malloc and horde malloc. In GPU systems, in CUDA, we often pre-allocate a certain amount of memory to serve all runtime memory need of a GPU kernel. However, memory consumption is unknown beforehand in many applications. This renders either over-allocation or terminating kernel due to the lack of memory. The typical approach to deal with this problem is to run the task twice. The first run is only for calculating the output size. Then the output memory can be precisely allocated, and the second run will finish the task. This obviously carries unnecessary overhead, and so a major challenge on GPU system is to dynamically allocate device memory for output results without interrupting kernel execution. So in 2009, NVIDIA released a dynamic memory allocator for CUDA, and that started a series of efforts on this topic, including xmalloc released in 2010, scatteralloc in 2012, FDG malloc in 2013, halloc in 2014, regf in 2015, dinosaur 2019, and Ouroboros in 2020. And a recent comparative study showed that Ouroboros outperformed all the other methods in both allocation performance and space efficiency, and so it can be considered the state of the art. So here is a quick overview of Ouroboros design. So Ouroboros divides the managed memory region into multiple queues, each serving a different page size. And instead of pre-allocating memory for the queues, the concept of virtualized queues were introduced. The main idea is that queues are dynamically stored on pages in the pool, and a new large page, which is called a chunk, is only allocated to the queue when it actually needs more space. In this design, the author avoided pre-allocating memory for all the queues. By using a semaphore, Ouroboros suffers from the long latency in accessing the queue state by concurrent threads. And it also creates significant memory overhead when request sizes are not close to the predetermined sizes, and significant latency when there are many requests of similar sizes. So we propose a core design called random walk. So we first assume that the GPU global memory is divided into pages of equal size, and each memory allocation request serve exactly one such page. And we will later relax this assumption. So the core technique is a random walk algorithm that does not depend on any global state to manage page allocation and recycling. Instead of using a few mutex locks or queues on global memory for the entire system, each page has its own mutex locks. That means that once the used flag in the page is set, it is considered not available. In requesting a page, each thread will generate a random page ID. If the corresponding page is free, the thread will get the page, and otherwise the thread will generate a new page ID until it finds one free page. And the main idea is we let all threads act independently, and therefore there is no need to wait in a queue for accessing a shared state. This releases the parallel computing power of GPU to a great extent. This figure shows an example of how 7 parallel threads get their free pages. Here the blue squares represent free pages and the red one represent occupied pages. Each thread repetitively generates random page IDs until it finds a free page. And if more than one thread select a page at the same time, one of them can acquire the page through an atomic operation while the other continue their search without waiting. And we will prove that the chance of this collision is low. And here's detailed implementation of the random walk algorithm. It's very, very simple. Although there's no global state, acquiring a free page still needs an atomic operation in line 4 because two threads can try to grab the same free page at the same time. So for example, in the previous figure, thread 5 and thread 7 both request page 8 at the same time. However, the atomic operation will only grant access to one thread, which in this case is thread number 5. And the other thread will have to continue its random walk. And this scenario is the only situation in which two threads can conflict in accessing protected data. And now let's take a look at the analysis, and we will show two things here. The first thing is we prove that the expected latency is lower than the queue design, and the second thing is we will prove that collision happens with a very low probability. So first, let's look at the metrics that we use for performance analysis. In general, latency is an appropriate metrics for evaluating performance. However, the actual running time is affected by many factors. So instead, we propose the following two metrics. The first one is called per thread average steps, TAS, and this is the average number of steps taken to find a free page for a thread. And in the algorithm that we showed, this is essentially the average number of iterations executed for the while loop in line 1. And while the latency of one step is not the same for all designs and implementations, we choose to focus on the number of steps in this analysis because it is a major indication of scalability. And the second metric is per WAP average steps, which is the average of the maximum number of steps taken among all threads in the WAP. So both of these metrics are directly correlated to latency. In CUDA, the basic unit of execution is a WAP, which is a group of 32 threads that are scheduled and executed simultaneously by a streaming multiprocessor. And the entire WAP will hold the computing resources until all threads in it exit. In other words, the latency of a WAP is the maximum latency among all 32 threads in the WAP. Our previous work showed that by measuring the average steps a thread takes, we can say that the running time is roughly a linear function of per thread latency. And we also verified that the effectiveness of the two metrics via the large number of experimental runs. And the results show that the correlation coefficient between TAS and the total running time is 0.9. And that for WAS is 0.96. And so this shows that WAS is a statistically better indicator of total running time. And both metrics are still good representations of latency. And here's the notations that we will use for our mathematical analysis. T is the total number of pages, A is the total number of free pages, N is the number of threads. So xi is the random variable representing the number of steps taken until finding a free page, and TAS is the expected value of xi. And y is the maximum number of steps to find a free page within a WAP. And WAS is the expected number of y. So first of all, we can easily show that this is in a queue-based solution. TAS EX is n plus 1 over 2, and WAS is roughly 32 over 33n. And the full proof can be found in our paper. And both of these metrics are linear to n, which is consistent with the result that what we showed earlier. And so maintaining multiple queues will not wipe out the issue. And it is easy to show that both TAS and WAS are still linearly related to the n, even if we use multiple queues. And in the case of random walk, here are the formulas for TAS and WAS. Again, the full proof will be found in our paper. And unlike the queue-based solution with latency linear to n, this equation tells us that the value grows very little with the increasing of n. So the first equation, under the wide range of n values, the logarithm term increases very slowly in a logarithm manner, and the increase of EX will be further offset by the inverse of n. And the only situation that could lead to a large TAS is when A is very close to n, which means that there are very little free pages available for the threads. And the result of these four equations can be showed in this figure. So here we plot the values of these four equations under different values of A and N, and T is kept at 1 million pages. So now we show that thread collisions happen very rarely. So thread collision is analogous to the well-studied birthday paradox. So let's say we have T birthdays, in this case pages, and n people, in this case the number of threads. And we would like to find the expected number of people who have the same birthday with at least one other person in the room. And so in particular, the expected number of collisions, as proven by a previous study, is n times n minus 1 over 2t. And this number should be small in a reasonable setup. So let's say with tens of gigabytes of global memory and a few thousand level parallelism in a modern GPU, we can safely assume that n is much smaller than the t. So for example, with 1 million pages and 5,000 threads, the expected number of collisions is only 12.5. And furthermore, the performance penalty only exists when the page is free. And so the expected number of collision is actually bounded by this term multiplied by A over T. So the basic random walk algorithm can be extended in several directions. First, we notice that walk is great when free pages are few, and we are aware of thread divergence among the walks. Some people can find the page very fast, and some can find the page very slow. So the first technique of optimization is called bitmap. Here we, in each step of a get page, each thread visits one page at a time, and so it can take many steps to find a free page, especially under a low A/T ratio. So we use bitmap to store all the used bit in consecutive memory space. In practice, the bitmap can be implemented as an array of 32-bit or 64-bit integer. So we can visit a group of 64 or 32 pages in a single read. And finding free page now reduces to finding a word from the bitmap that has at least one unset bit. And such an algorithm can be easily implemented by slightly modifying the first algorithm. And so we did a analysis of this algorithm and showed in our paper that SWAS for this algorithm are as on the screen. And how good are the terms? Well, we proved two theorems. The first theorem says that so if we let Uprime as the TAS for the bitmap implementation and that for the basic random walk algorithm, then we have that the limit of Uprime is equal to U over W. Here W is the number of word, which is 32 or 64. And this limit, this approach the limit when the number of free pages approach the n, which means that when the number of free pages are really low. And similarly on algorithm 2, if we let v prime as the upper bound for WAS, and that for the basic random walk algorithm is v, then we have that the limit of v prime is about v over w. And these two theorems are very encouraging because both TAS and WAS bound decrease by a factor of w, which is 32 or 64 depending on the implementation. And so the advantage of RWBM is the highest when A approaches n, which is the extreme case of low page availability. And here is the experimental result that verified these two theorems. Here we performed experiments on different levels of free pages, and the lower the percentage of free pages, the ratio of the speed up of the bitmap implementation over the basic implementation approaches 32, as you can see here that it moves from the black line to the red line. And the second optimization technique that we take is called random walk. So the basic RW design suffers from large difference between TAS and WAS. And to remedy that, our idea is to have the threads in the same warp work cooperatively. So threads that found multiple pages from the bitmap will share the pages to others that did not find anything. And this can effectively reduce the longest steps of RW by the threads in the warp. So this algorithm repeats two steps. Number one, the threads work together to find free pages, and number two, identified free pages are and assign them to individual threads according to their need. So implementation of this idea is not trivial. The main challenge is to keep track of the found pages and distribute them to requesting threads. And So in this algorithm, a need mask is a 32-bit mask that represents what threads still need to get a page, and hash mask is the mask that indicates which thread need or has found a page. So we perform this search process on all threads until we obtain a page, until all threads obtain a page. That means that the need mask becomes 0, like on line 4. This process is repeated as follows. First, each thread reads a random word on the bitmap, like on line 7. And then a key innovation is that if the word was already locked by a thread, then we cannot use the word as a source of free pages, and instead of idling and waiting for it to unlock, we will return a word with all bit sets and continue the rest of the loop without acting as a consumer of free pages. And then from line 9, we share the free pages among threads. And while some threads still need to find a page, and some threads still has a page to share. And this is difficult because the CORW shuffle instruction only allows a thread to read the data from another thread. And so the receiving thread has to initiate the transfer. And so our solution is to calculate the sending lane ID T param as follow. So each thread calculate the S, which is the number of threads with lower lane ID that still need to get a page as indicated by need mask. And then this thread has to obtain the S plus 1 page found within the WAP, because the first S pages should have been given to the lower lanes. And so T prime is the position of the S plus 1 set bit on hash mask. And here's the example of 6 threads sharing their request. So since thread 1, 2, and 4 filed 6 pages together, we can serve all requests in one round. Without CORW, thread 035 will have to access the bitmap again. And now we talk about memory allocation. So our work on the bitmap and the collaborative random walk paved the way toward allocation of consecutive memory of an arbitrary size. And we named the function RW_malloc. And so we still divide the memory pool into small units of the same size and store the used bit in the bitmap. And so the problem of getting X byte by RW_malloc reduces to finding X over S consecutive unit, where S is the unit size. So RW_malloc can be viewed as an extension of CORW. However, instead of each thread reading a random word, here we have all threads in the WAP read consecutive words to get a large region in the bitmap. And then each thread will scan a small part of the region to find all consecutive unset bits. So here 3 segments running across to neighboring words are also connected. And critical information such as starting position, length used or not used of all 3 segments are stored in local register. And finally, threads use shuffle instructions to read all 3 segments found within the WAP and find a free segment that can serve as malloc request. And as compared to collaborative random walk, the main innovation here is finding a range S and L of consecutive unset bit on a word as computed on line 7 and line 22. Where S is the starting position and L is the length of the unset bit. And here we only need to find the first of such ranges shared among the WAP and find the next range and repeat. And finding the unset range can be done very efficiently by using the intrinsic functions. And due to the fast scanning of the bitmap, RW malloc inherits the good performance of RW bitmap, and as multiple bits can be visited at once. And as compared to collaborative random walk, the cost of RW malloc is higher because we have to read all segments in a WAP to find a suitable one. But since all data are already stored in registers and shared by shuffle instructions, the overall performance is still much better than the queue-based implementations. So let's talk about experiments. So we perform experiments to compare our methods with Ouroboros, which is the state-of-the-art memory allocation. And we use, in all experiments, we configure both Ouroboros and our systems to have a total of 8 gigabytes in memory pool and to serve the maximum request size of 8 kilobyte. Each chunk in the Ouroboros system is 8 kilobyte, and there are 10 processing queues. And on our side, we evaluate random walk without bitmap, random walk with bitmap, collaborative random walk, and RW malloc. And we for metrics we use TIS, WAS, and TAM. So in this figure we show the metrics measured from the kernel as well as theoretical values of TAS and WAS generated from our analysis. And the result from the first row shows that our collaborative random walk outperforms Ouroboros by more than an order of magnitude under the most of the cases. When there are less than 1% free page, the advantage of our method starts decreasing, but collaborative random walk still outperform Ouroboros by a large margin. And the result from the second and the third rows confirm the validity of our theoretical results. First, the measure TAS values match the theoretical results very well, and the theoretical upper bound of WAS match the experimental result well under 1% of free pages, which indicates that the bounds are tight. And the bound becomes loose as the percentage of free page decreases to below 1%. And here's the performance of RW malloc versus Ouroboros when scaling the number of threads. So here RW malloc is faster than Ouroboros by up to 3 orders of magnitude, and the improvement is higher as the number of thread grows, except for 8 kilobyte of allocation, because this much allocation depletes the memory pool and bring our system into the worst scenario. And similarly, RW malloc perform better in freeing memory as the number of threads grow up, and by up to an order of magnitude. This kernel, this figure shows the total kernel running time when the allocation size scales. So Ouroboros performance decreases by more than an order of magnitude when allocation size increases from 4 to 8 kilobytes. And random walk malloc is insensitive to the change of allocation size. So in this figure shows the total kernel time when the allocations size is mixed. This figure shows that RW malloc outperforms Ouroboros in allocating a wide range of memory sizes, and the improvement reaches 2 orders of magnitude in the best cases where there are the most number of parallel threads and most free memory unit in the system. The higher the concurrency is, the better RW malloc outperform Ouroboros due to Ouroboros linear scaling. And RW's malloc performance degrades as fewer memory units are available. However, it is still much better than Ouroboros in its worst scenario when there are almost no free pages. And actually, the only case when Ouroboros wins is when it immediately frees memory just allocated. And by this, Ouroboros hit a sweet spot since it does not need to allocate new chunks to extend the virtualized queues. However, we believe this is an unrealistic scenario as buffers will normally be used before it is released. And we also evaluated memory utilization, SAM. So here we keep sending allocation requests until a system reports an out of memory error. And the memory utilization is calculated as the fraction of total allocated amount in the entire memory pool. And we perform this experiment with various unit sizes while maintaining the fairness between Ouroboros and our system in terms of total memory and maximum allocation size. And here, our memory utilization of RW malloc is always close to 100%. And on contrary, Ouroboros perform well when allocation sizes are some power of 2, because these sizes fit perfectly into the pages. So the reason is that our system allocates large memory chunks by aggregating small consecutive pages, and so has a finite granularity or control over the memory space. So in conclusion, so we studied the problem of runtime memory allocation in highly parallel software system with a focus on GPUs. The main idea of our design is to avoid maintaining metadata that could become a major bottleneck in a high concurrency system. Based on that philosophy, we proposed a memory allocation design based on a random walk mechanism and have proven mathematically that RW can significantly outperform the queue-based solution under most scenarios. And to address random walk limitations, we propose two advanced techniques. The first one is based on the storage of page information in a bitmap. And this is shown to improve the latency of RW by a factor of 32 or 64. And the second one involves the sharing of free pages among neighboring threads. We also present our solution to problem of allocating arbitrary bytes. Our experimental results are consistent with the mathematical analysis, and the results show that our solution significantly outperformed the best known GPU memory allocation, Ouroboros. And furthermore, we demonstrate a case study by integrating the page allocation code into a state-of-the-art GPU-based hash join algorithm. And our idea provides a framework that can be extended into accommodating a wide range of algorithms to gain better performance under different scenarios. So more aggressive random walk approaches can be designed and analyzed. So the random walk malloc design still has its limitation. So for example, for supporting very large memory requests can be interesting research topic. Thank you.